get feedback. You're recording. Excellent. Good. Yes. And here is the blue thingy bit. Wonderful. And I share my screen because I've got my prompts there. And here we go. And Bernardo just took the words out of my mouth. It's the Moodle attendance, which is open now. And I thought that in this session today, we will actually discuss a little bit this attendance thing. Because I think that's quite interesting. And my feeling is that sometimes you get things a little bit sort of only one side of the coin reported. But I don't want to get you too excited and overact the anticipation thing. You are all aware that you have another program level multiple choice quiz tomorrow. Are you aware of that? Good. Unfortunately, yeah. And for those of you who are doing the BI 300 module, and I know it's not everybody who is doing that module, but for those of you who are doing the BI 300 module, I posted some practice questions on a website. Have you guys seen this website? Have you received this post? Yes. No. Okay. It was, you should get it through the email because I put it into the announcement BI 300 on Moodle. Okay, what I'm going to do after this session, I will head over to SDS and I will send out a general email with a link to these practice questions. And then you should not have any problems. And to answer Darius' question, week 6 of BI 308 included in the MCQ, the answer is very simple, no. Because BI 308, this module here, the skills module, is not part of the MCQ tomorrow. So for the MCQ, the stuff that we have done together, you best need to ask the module convener what is covered in the MCQ tomorrow. And the module convener is my lovely colleague, Dr. Chris Mulligan. What modules are part of it again? I don't want to say anything stupid. I know that BI 300 is part of the MCQ. And I know for sure that BI 308, this skills, what we are doing today, is not part of the MCQ. Yeah, and Konrad just confirmed. 300, 302, and 324. Okay, so, and it's 5 past, so please don't forget to register your attendance on Moodle. Keep yourself muted, please, because otherwise the clown watch will be active. And let's get started. Today is hopefully not too strenuous. But I think it's important that we sort of have still a quick recap of a regression, correlation, and standard curves, because this is the stuff that's really, really the bread and butter of any bioscientist. So in the last session, I think that was last week. Was it last week? Yes, it was last week. I discussed with you in general correlation. So correlation. And we usually would work with linear dependencies. So you would have usually something like that. On the x-axis, you plot the independent value. And please keep yourself muted, because I know ClownWatch is active again. So on the x-axis, it's the independent value that you have control over. And on the y-axis, you have the values that result from the independent. So these are the dependent values. And ideally, we would like a linear relationship. So something like that. Where we have data, ideally something like that. We will come across cases where we don't just plot the dependent or the independent. We can do transformations, and I showed you on the workshop on when was that? On Tuesday. I showed you that when we, for example, measure the distance of DNA fragments in a gel, we would, when we do a sort of a standard curve, we would, for gels, we would plot the log of the fragment size versus the distance traveled. So it's perfectly acceptable to do transformations like logs or like one or reciprocal values or something like that. And we will go into more detail then in next term when we talk about enzyme kinetics, where we again have these transformations. So here, what we usually would like to see is such a correlation. I also showed you that we can make a statement about the quality of the correlation. And I introduced to you the Pearson's R. Pearson's correlation coefficient, which is usually R, or sometimes it's capital R, it doesn't matter. The R value can sit between -1 and +1, and it tells us how good the correlation is. I told you that, for example, an R value of larger than 0.9 would be considered as a strong correlation. a positive R value. So if the R value is positive, it means we have a positive correlation, and the dependent and independent values go in the same direction. So in this case, this would be the graph that I drawn here. Is that a positive or negative correlation? Positive or negative? Yep. Yep, it is a positive correlation, because the larger the independent values, the larger the dependent values. Absolutely right. So that's pretty straightforward. And when we look at, for example, the R square value, this has actually a practical meaning. It just simply means the percent of dependent values that can be explained by the independent values. By the independent measurements. So if we've got, say, an R value of R square value of 0.9, this means 90% of our dependent values are actually exactly on this line of best fit. I showed you how you can do that in Excel, the line of best fit. And when you do that in Excel, you then also can ask the program to calculate the correlation coefficient. But if you don't want to plot the graph, and it's always a good idea to plot the graph, just to see what's going on. But if you want just a quick check for the correlation coefficient, the command in Excel is, I think it is Correl, and then it asks you for the X values, the Y values, and then the X values, and it will spit out the Pearson's R. So that is something that we have done more or less. I want to make a few comments about linear regression, because oh God, even my program has problems today. Let's draw that nicely. Okay. So let's say we do a linear regression. So here we have our X values. Here we've got Y. And we get these data, something like that. Okay. Now, when we use a standard curve, and you have done standard curves, you've done standard curves for your glucose concentration. There, and you can see a standard curve is a sort of a special case standard curve is a special case of a correlation, because we use the standard curve then to look at Y values and then try to estimate unknown x values. But it is a correlation. And when we are talking about standard curves, there's one thing that you must not do. So for standard curves, when you use a correlation as a standard curve, never extend. Hello, good morning. Never extend. So your last measurement really is the end of the standard curve. And if you have a measurement that is outside the standard curve, let's say you've got something like here, or you might have something up here, these are measurements that you cannot use for your standard curve. It is how shall I say, it is a crime against good laboratory practice to use values outside a standard curve. You are not allowed to extend it. That is strictly taboo. That is forbidden. Never do that. And of course, when you do measurements with a spectrophotometer, your Y values, where you measure the absorbance, it must always be smaller than 1. If you've got something larger than 1, you can't measure it properly anyway. So that might be helpful when you look at your experiment for the honey practical. It would not necessarily go through the last point, because you could have, let me remove that so that you can see that better. So if you've got, let's say, a value like that, and we are trying to do just drew it through, but your line of best fit might be like that. So it does not necessarily have to go through the last point, but you cannot extend it. It would end where the last point actually is, here. And here it would be this one here. But you can't extend it. So never do that. Okay? So when it comes to general correlations, so that is for standard curves, never extend it. But when it comes to general regression or linear regression, let me try that again. Extending is always dangerous. Extending is dangerous. In standard curves, you can't do it. In a normal linear regression, where you've got something like that, let's see if I can do a good line of best fit. Extending this line, when it is an ordinary linear regression, is occasionally permissible. This is then called forecasting, which is basically you try to make a prediction how a value will be if you extend it like that. But it's very, very dangerous to do forecasting. I give you an example. The one that I absolutely love, and I hope I don't offend anyone, If anyone feels offended by it, then this is not my intention. But it's a really nice example. So I dug out some statistics, and I unfortunately didn't write down where I got it from, but I see if I can find it again. That in the last 20 years, so from 2000 to 2020, the obesity rate in the beautiful state of Alabama went from 15% to 35%. Okay, and the great thing is that that's why I chose that. If you look at it, do we have anyone from Alabama here? Who might feel offended? No. Oh, that's good. So it is basically, if you look at it, it went up by 20% in 20 years. You're from Arkansas. I better not say anything. I heard it's a lovely place, Arkansas. I've never been there. My only visits to the States were, interestingly, New Mexico. But please keep it clean. So in 20 years, the obesity rate went up by 20%. So if you now extend this line and say, I want to know what is the obesity rate in the year 2100. What would be the obesity rate in 2100? If you just simply extend. James, you're absolutely right. It's 100. No, it's not 135%. It would be 115%. 115% would be the obesity rate. Wait a moment, let's think about that. What does that mean? It means that 115% of the population of Alabama would be obese. 115% of the population, not 100%. 100% would mean everybody in all Alabama is obese. That's 100%. But what are these 15%? Reynolds? Absolutely right. It does not make sense. Absolutely right. And therefore, you see the problem with forecasting? Well, if it starts with 15% in the year 2000 and it increases 1% per year, in the year 2100, you've got 100% plus 15%. It does not work. Exactly. You can't have 115%. This is where the forecasting does not work. No, I'm not calling them super fat. It is obese, just obese. Obese includes everything. So 115% means everybody is obese plus, well, maybe the cat, the dog, I don't know. But it doesn't work. So forecasting is dangerous. Do not really try to forecast unless you know exactly what you're doing. No, it doesn't. No. It's not more. It's not a quantification of the being obese. It tells you how many people are obese. And with this forecasting, it would be 115%. It's absolutely not. Right? So forecasting, be very, very careful. Let me draw it like that. When you do forecasting, you really need to know what you are doing. Yes? The most likely scenario is that if you've got these data here, what it will look like is you've got probably a good start like that. And what you're looking at the moment is this part here where it's linear. But then this curve will flatten and probably plateau off. You just don't forecast. Exactly. 115% would include everybody plus 15%, but that doesn't make sense. That's the whole point, what I'm saying. And what it probably would look like is if we've got 100% here, this is what this curve actually probably looks like. So here would be 2020, right? Here would be 2000. At the moment, you see the linear part, this bit here. But if you wait long enough, it will plateau off. If you just said, okay, I just simply forecast, it would go like that. So what you are doing here is basically you make a big mistake in your forecast, and that is where forecasting really falls down. You could forecast until you reach 100%, but think about it. Would 100% be actually the limit for your forecasting? Absolutely right. Would that be the limit? Or, because even newborn babies would be included in that, in the population, and usually newborn babies are not obese. Okay, I'm not getting into this discussion about Alabama. I know some people from Alabama, and they are really absolutely lovely people. The point that I want to make is forecasting is dangerous, very dangerous, and yet we live on the basis of forecasting. One of my friends runs a business where they are trying to do forecasts about the use of energy during certain times of the day and over the year or something like that. So he is an advisor to the national grid and says, well, we've got this weather forecast. Weather forecasting, for example, is another one where we use linear or non-linear models. So we need to very often we do forecasting, but I just want to point out to you, be very, very careful with forecasting, right? Does that make sense? Exactly, you know, you use forecasting in every day, but you need to be careful with what are the limits of your forecast. How trustworthy is it? So really the take-home message is, and Reynolds, I could not say it more succinctly, be careful. You can do extrapolation, but be extremely careful with the extrapolation. Another thing that I want to point out to you is very often people believe that a correlation tells you something about the cause of something. So this is correlation versus causation. And that's a very important phrase. Correlation does not equal causation. What do I mean by that? So, for example, in the 1960s in Sweden, scientists looked at the number of breeding storks. You know the stork, big white bird. And in Sweden, you see them nesting. And they did a correlation and they checked the number of babies born during the same time. And they found that there was an almost perfect correlation between the number of babies born and actually this is not true what you say, Konrad. Storks don't abduct children. It's actually exactly the opposite, because folklore has it that the stork delivers babies. They bring the babies. And if you want proof of that, watch the Disney movie Dumbo, where Dumbo is delivered by a stork. So the stork delivers babies. And this analysis, scientific analysis, actually, this, if you look at it, it looks like that there is a very strong positive correlation between the number of storks and the number of babies, and therefore a very quick causation would be that the more storks you have, the more babies are delivered. So storks deliver babies. And of course, very often these graphs are used to make a case that there is a causation. And a lot of people just simply see, oh, wow, look, there is a really good correlation. So therefore, this claim of a causation must be true. However, it is very often incredibly difficult to establish a true causation. And this is something that has occupied the courts for many, many years. Because if you look at, for example, the number of cigarettes smoked, and the incidence of lung cancer. What would you expect? Would you expect a correlation here? What kind of correlation? You expect a positive correlation. Is it linear? That's a good question, actually. For the time being, let's assume it is linear, but that's not necessarily a given. So we might have something like that. So then people or the relatives of people who smoked and then died of lung cancer, they went to the courts and says, we want to sue the tobacco companies. And here is the evidence. Smoking causes lung cancer. Smoking causes lung cancer. And the judges looked at it and said, yeah, it looks like a really pretty strong correlation. The lawyers of the tobacco companies said, yeah, there might be a correlation, but you cannot prove that there is causation. You cannot prove with that, no proof that there is, that lung cancer is caused by smoking, that there is a causation. And this went on over many, many years. Everybody knew it, but there is no proof. Because, and we know a lot of cases or a lot of examples where you have what might be a spurious correlation, like with the storks. Spurious correlations. Exactly. There are people who smoke who don't have lung cancer. There are people who have lung cancer who've never smoked. Yeah? And still, this correlation does not prove anything. And as I said, there are spurious correlations, like, for example, the storks. Or there is a fantastic website. It's the website of Spurious Correlations. So, for example, you see an almost perfect correlation can I increase this a little bit? I don't know. You probably see that there is a very good correlation, a 99.8% correlation coefficient between the US spending on science, space, and technology and the number of suicides by hanging, strangulation, and suffocation. And you see there's a fantastic correlation. If you look at the example below, number of people who drowned by falling into a pool, and it correlates with the appearances of Nicolas Cage in movies. Look at that. It's not a perfect correlation, but it's still a good correlation. That is actually an interesting point where what Conrad actually says. I absolutely agree with you. Some people would be really worried about that. Per capita cheese consumption, number of people who died by becoming tangled in their bed sheets. Again, you see a fantastic correlation. You have to ask them in the afterlife. So there are these correlations, right? And is there a causation? Probably not. But we need to be really aware of these spurious correlations. And sometimes, actually, there is a correlation. And this is caused by something else. By something else that we are not that we are not at the moment measuring. This is called lurking variables. These are variables that we haven't measured, but these variables actually affect the x and also the y values. I give you an example for that. If you plot the number of ice cream sales versus the incidence of skin cancer, you would find that there is a pretty good correlation. So obviously, does that mean that the more ice cream you eat, the more likely it is that you get skin cancer? Hopefully not. Or does it mean that people who suffer from skin cancer eat more ice cream? Hopefully not. But is there something that sits sort of in the background that we haven't measured here, that sits in the background that affects ice cream and that also affects skin cancer? Is there something? Sunshine, UV. Temperatures. So this would be the lurking variable that affects both, but that we are not measuring at the moment. Right? So the warmer it is, the more ice cream is consumed. Warm temperatures up would usually mean more sunshine. More sunshine means more UV. People dress lighter, and therefore there is a correlation between ice cream and skin cancer, but it's not directly caused by each other. There is this lurking variable in the background. Absolutely right. The lurking variable is the hidden link. Exactly. Right? Now, you also have been told I think that's the right approach. That's absolutely the right. There is no problem on this planet that cannot be solved with ice cream. And we could do a quick poll of what is the favorite ice cream flavor. Now, well, with UV, you would not necessarily affect the proteins, you would affect the DNA. Dark chocolate and mango. Last mango in Paris. Yes, absolutely. I go with that. Dark chocolate, vanilla, all the way. Good. I think I got you guys. There is another thing where you have, I don't want to say being missold things, but where very often people present you with a correlation. Let's see what you think about the following. We do, let's say, attendance in lectures. And attainment, let's call it attainment, which basically means marks in exams, marks in degree program. And people always tell you that there is a very strong correlation between the attendance in lectures, and I draw it like that, and the grades that you get. Have you heard that? Very strong correlation between attendance and attainment. Mm-hmm. So people have heard about that. And people say, because of this, we have to measure, we have to monitor attendance, because the better the attendance, the better the grades. It makes sense, doesn't it? Obviously. Could you, and I agree, very often if students show low attendance, it indicates that there might be a problem, right? But could you think of a lurking variable? Could you think of a lurking variable that leads to this correlation between attendance and attainment? Hmm. Tiredness, laziness, lack of interest. Give it a positive phrase, Reynolds. I think that's a really, that you are onto something. Make it broader. Make it broader. Motivation, for example. So interest in the program. So motivation could be the lurking could be the lurking variable between it. The more motivated you are, the more you will attend the lectures. Engagement, exactly, yes? Absolutely right, yeah? So I just stick with the motivation theme. The more motivated you are, the more excited you are and go to the lectures. And therefore, you will also read around the subject and therefore will get better marks. Does that make sense? Inspiration, yes, absolutely. There could be a lot of inspiration, yes. Life issues. Although, and you can come up with loads and loads of potential, so lots of potential lurking variables. All sorts of things, disabilities, things like that. It can all uh, go in there. It can also be a combination of all these things. And in a way, this is now when you establish something like that here, when you get a curve like that, or a straight line, or a correlation like that, this is not the end of the work. This is the beginning of the work as a scientist. Because as a scientist, you need to say then, right, I get a strong correlation. I get a strong correlation here. And now, as a scientist, I need to find out what actually causes it. What are the lurking variables? Is it just one? Is it a combination of lurking variables? And one way of dealing with that is a method called multiple regression, where you do measurements of these variables then, and you combine them and try to figure out how do they work together in affecting attainment. Multiple regression and principal component analysis. These are then methods that with which you can try to address actually these lurking variables and combinations of lurking variables. I do not expect you to know about these things. I will not ask you about that in any shape or form. I just thought this is really interesting. And if you want to look or get more information about these things, there are lots of YouTube videos out there where you can do a little bit of further reading, but I'm not going to ask you about that. I would be very happy if when asked, you could explain the principle of a lurking variable to me. Does that make sense? So as a scientist, whenever a correlation is presented to you, what I really want you to do is say, wait a moment, is this a correlation? And what, well, it is a correlation, but what could be the lurking variables that actually dictate this correlation, that determine this correlation? Are you happy with that? Does that make sense? So be aware of correlations. There is a lot to it. Before I finish, I have a note here which says practicals. And I know that we are now in lockdown 2.0. Some people have gone home. Some people are still going home. They shouldn't go home, but and they are worried about the practicals. What if I can't do the practical, the face-to-face practical? Well, all our practicals have been designed that the learning outcomes can also be achieved through the online versions of the practicals. So if for one reason or another, people who are supposed to do the face-to-face practicals cannot do them because they are self-isolating, they are gone home, they are studying remotely or whatever, there's always, for each practical, there's an online version for the practical, and the learning outcomes are covered by the online version of the practicals. So you are strongly encouraged to do the online. You do the online version. If you are at home and you cannot attend, please let bioadmin at Kent, ACUK, let them know there is, if you want to study remotely, so without attending the face-to-face, there is a form. You just fill in this form, and so that we know that you are studying remote. And that then will be absolutely fine. Okay, so let people know that you are not around. You also might want to put in a claim on the concessions site on Faramir. And we will look at that and say, yes, fine, we know that the student is not around. We know that the student is self-isolated. We know that the student has these issues. So not a problem. But please do the online version then, online or version of practicals, because that then covers the learning outcomes. And that's what you're here for, to learn. Does that make sense? In this case, if it is only for a period of time, just let bioadmin know about that. And they will then make a decision whether they ask you to fill out the form or not. Absolutely. Yeah, Alessandra is right. I mean, the more we communicate with each other, the easier things are, and the better things will run. So what I'm going to do is I will send out an email to these practice questions for the BI 300 folks. So please check your email. I know you are inundated with emails, but please check the email. I've set up a website where you can do practice questions for BI 300. And I'm going to set up practice questions also for BI 308. Would people want that? Do people want practice questions for BI 308 for the skills? Okay, consider it done. Thank you very much for watching, and I shall see you tomorrow afternoon for what I think probably will do a little bit of a recap and revision of the last 6 weeks to give you an idea of what I want you to know. Be good, don't do anything I wouldn't do, and don't overdo it with the ice cream, because you know that there is a strong correlation with skin cancer. So see you tomorrow. Bye-bye.